Okay. So, oh yeah, what we have seen is if you have a solenoid, and when I say a solenoid, I just mean an infinite solenoid. What we have seen is this BZ approaches 0 as what? Maybe I can use cylindrical coordinate system, right? It really doesn't matter, but S approaches infinity. And we have also shown that there's no B phi and what's the other one? BS, right? They're 0. So now, armed with this, you can use Ampere's law to easily calculate the magnetic field. Okay, what is Ampere's law? Closed loop, B dot dl equals mu 0 times I enclosed. So then, I'm going to take a simple loop like this. And for this particular loop, there's no B here and B here. So let me call this S2 and S1, meaning the distance from the axis. Yeah? So BZ evaluated at S2 minus BZ evaluated at S1. And let's say I'm going to integrate it through some height. This cannot depend on position because it's an infinite. So BZ is constant here, BZ is constant there. So times H. But that's equal to 0. There's no current over here. So that means outside the solenoid, BZ S2 equals BZ S1. Now I let this go to infinity, or that go to infinity, doesn't matter. And we have shown that it goes to 0. That implies so in a perfect solenoid, there's no magnetic field. Perfect, infinite solenoid, just an entirely an abstract mathematical quantity, there's no magnetic field outside the solenoid.
How do we not prove BZ goes to 0 at infinity? We would have only been able, because we know there's no current on the outside, we would have only been able to say that.
No, remember we did the calculation.
No, we did, but
yeah.
how do we have not? Like, I'm trying to understand why we did it, so to speak.
Right.
And if we had not done that,
right,
then we would have just said, well, they're equal, so they're constants.
They're constant.
We wouldn't have known that
whether it's 0. Okay. Yeah. And you can say, well, infinitely far away, everything goes to 0. That's almost true, except this is an infinite solenoid. For example, if you have an infinite plane of charge, uniformly charged, then it's sigma over epsilon naught. It doesn't go to 0. Now, one could use an even more sophisticated argument that a solenoid is like a line, and it's not a plane, so it goes to 0. But that would just be a heuristic. And the calculation yesterday was good to see. Whenever, not necessarily you remember, it's good to have it even archived in your notes and understand, whenever you have a problem to show that certain terms must go to 0 during symmetry, use a symmetry argument, but if you cannot really pin it down, set up the integral, you'll see that it goes to 0 if indeed your thinking is correct. Chip,
I think I'm just missing something.
where? So I'm taking this loop. I already know there's no B here through this direction because the S component is 0.
Mhm.
So B, if it exists, only exists here and here.
Yeah.
And if it exists here throughout the entire length, in fact, throughout the entire line, it would be a constant because this is an infinite solenoid. I mean, it's a tube in the entire universe, right? So it has to be a constant. It cannot depend on Z, so to speak. So too here, it must be a constant. So B dot dl becomes B times some height. You're integrating the loop over. But there's no current here. You're setting it equal to 0. So whatever it is, B outside the solenoid must be a constant. And since it vanishes at infinity, it has to vanish everywhere. Yeah? Okay, so now let's hope, not hope, let's imagine the current goes this way, meaning like this, where the current comes out over here. Why? I'm trying to calculate inside the solenoid. Well, I need a new Amperian loop. So I will pick a loop like this. And my current is flowing into the board. So this is the direction of the current. So that means I have to integrate this way for Stokes' law. So yeah, because the current is flowing in. So then, only then if I do this, I get that. Okay?
I mean, we picked two parts where, like,
One is inside the solenoid.
specifically is, yeah.
One is inside the solenoid, one is outside the solenoid.
Uh-huh.
Yeah. So now the contribution happens only along one of the four portions of the curve. Which portion of the curve does the contribution come from? In terms of this integral, we know there's going to be a current. So I can do it this way. If I pick some length L, I know the right-hand side is mu0 times current times number of windings per unit length times L. That's the total current enclosed, right? So N is windings per length. It's a W. So I know this is what it is on the right side. I know on the left side, I'm not really going to integrate. I'm going to have an L. Well, the only component here is going to be that. There's no component in the S direction. So just like Gauss's law, once you have determined things from symmetry, now writing the field is just trivial, and B equals mu0 n I. If I want to write it vectorially, for this particular configuration, sometimes Griffiths even writes after all. That's not fair. No, let's not do that because the current itself is in the phi direction. This is the perfect solenoid. The current simply goes straight through. The magnetic field simply points uniformly inside. It doesn't depend on how far away from the center it is. There's no S dependence, nothing. We know there's no S dependence. Yeah? Okay. Now what about a real solenoid? Well, inside the solenoid, we would get this P that looks like that. Right outside the solenoid, there might be some fringe effects. Just over here. And it weakens as, you know, I'm not saying it's just, and as the further out you go, the magnetic field just weakens radically. And over here, it's uniform. So now in the interior region, even on a finite region, if you play around numbers carefully, at the center in one location, you can make the magnetic field constant and the change of magnetic field, meaning the magnetic field is almost constant in the region. So to conduct an experiment where you need a constant magnetic field, it's easy, just create a tube. So in a particle accelerator, for example, it's a uniform magnetic field. You throw in a particle, it'll just circle around it, like in a particle accelerator. Except particle accelerator is not a straight tube. You want to collect the particle at the other end. Yeah? So what do? This is the next example. I cannot draw this picture. So let me draw a simple version. First, imagine if it's a donut. Yeah? And ooh, did I mess that up?
I can see it.
Somewhere there's a, I don't need these two guys, right? And the wires are wound this way. Okay? So it is some, so in this case, you have n total number of windings, a winding number. Now what I want to do, just like I have shown that Bz goes to 0 infinitely far away, you can argue from symmetry, and Griffiths just puts up this integral. There's no particular insight that you can see from it, but I would urge for you to look at it. This is on page 238, and this is example 510. In fact, the argument I'm saying is on page 239. And he argues that the only magnetic field that will exist is in the phi direction by symmetry. It's just like my integral problem. You have to set up an integral of sorts. It is not difficult to follow. It's just that you have to be patient.
So is this like
It's a donut.
is it a solenoid?
It's a solenoid.
Like
Wrapped like that, yeah, with very tight winding. Yeah, and when I say a donut, you might think a circular donut. It doesn't matter what the shape is. It can have any arbitrary cross section. imagine, if you will, you take, you know, this sort of a cross section, but you wrap it around. This shape does not matter, just the way you set up the integral. B is going to be yeah? So all of you have pads. Turn to the Griffiths page 238 to see the picture. Okay? It can be, and the integral is not complicated at all. In fact, you don't even, it's not an integral, he just sets up the expression for the magnetic field using Biot-Savart's law. Okay? And he doesn't even set up the integral. You can just look at it, and you'll see that if you're looking at any other component outside of phi hat direction, the one component, you know, one side of the donut is canceled by the other side of the donut. That's what happens. Okay? It's a little bit of a strain. Make sure you've had your morning coffee before you just look at the terms. Yeah? But this comes around. Now we know that we can use Ampere's law.
Would that same cross-section argument apply for our infinite solenoid?
No.
It would lack a
No,
certain amount of
because
symmetry.
it'll-
It wouldn't have- this has intrinsic circular symmetry.
Circular.
It wouldn't have it.
Right. Yeah. Yeah. Meaning you couldn't have a hyperbolic solenoid. Because here, BZ is not going to be constant. So, again, this is why I would love to take an art class to draw that diagram. So here is my center, and what I'm going to do is pick the center of the, or any point inside, yeah, any point inside the donut, for lack of a better word, and from symmetry, it's constant along the loop. So this just becomes B times 2 pi S. And the current that is enclosed is mu 0 times I times N, all of it, because you're making a closed loop. And so the magnetic field this would be inside, and of course B equals 0 outside, because if I pick somewhere over here, and if I do a loop, there's no current going through it. Once again, in this case, because of the rotational symmetry, we don't need any other symmetry in that cross-sectional plane. It's just a bizarre feature that it works out exactly right. Yeah, the argument itself is not hard to follow. So now you have a legitimate particle accelerator. You can have things go around, come back to itself, and keep doing this, and then it collides with another charged particle and see what comes up. That's what a particle accelerator. It's a particle collider. Yeah? Melissa, good with visualization? Chip?
Where do we get our S?
Yeah, so
I mean, you said something.
So suppose, imagine you have a donut. Let's just make it a donut. And there's the center of the donut, the z-axis. And then from, or any cylindrical center from the z-axis. And you draw it all the way to the inside point inside the donut. And then you go a complete loop. But regardless of S, you can go further out and for a little bit in if you want. The current is you're capturing all of it, mu 0 times N times I, because you're going through a closed loop, and so you're catching all the windings. On the other hand, Here now it is S dependent. If you're closer to the axis, the magnetic field is stronger because it's inversely proportional. The further out you are, the magnetic field is weaker.
So inside means inside of the hole.
Inside the donut.
So it's outside of the donut.
If inside is inside of the donut.
Yeah,
Like
but
inside the hole.
The meat of the donut. Oh, not inside the hole.
Yeah, that's what you.
Okay.
Yeah. Oh, that's a good point. Yeah. Where you can taste the donut is where the magnetic field is.
Okay.
Yeah? Donut it's a curious object. What's the central mass of a donut? It's in the center of the donut, right? Is there any mass there? If you want to define something to be curved, a surface to be curved, a flat sheet of paper is not curved. A sphere would be something that is curved. What about a donut? A donut is a flat surface because you take imagine it's made of paper. Slice through it, spread it out, it's a flat sheet of paper. It has no intrinsic mathematical curvature.
Is that how mathematical curvature is defined?
One of the ways. There's a way using perhaps geodesics of sorts. Yeah. Okay. Right. So we have seen that divergence, so this is called the vector potential. This section, if you will. In the case of electrostatics, you had a scalar potential, the electric potential, just a function, what do we call it, V? Here, you won't have that. So, because it's the flip, divergence of B is 0. We have seen that from Helmholtz's theorem, divergence and curl prescribes a vector field. And here it is, divergence and curl. And a vector field is in general given by the gradient of something plus the curl of something. But the divergence of the gradient is not 0. It's the Laplacian. But the divergence of the curl is always 0. So, in that case, B, and this is the definition of vector potential. I suppose I should have said the magnetostatic vector potential for the moment, and that is nothing more than a vector field A such that its curl gives B. Again, let me clarify. Then divergence of B is equal to divergence of curl of A, and we know that the divergence of curl of any object is 0. And that's why, from the Helmholtz choice, you can pick the curl term and say that the gradient term doesn't exist, because it doesn't have to be 0. Yeah. Okay, so what I'm going to do is take this and stick it back in here. because potentials have a way of making life easier. So let me recall. So we have divergence of E is equal to rho over epsilon naught. And we picked E to be, and for convenience, so that we have an interpretation of potential energy, we call it V, sorry. And so then I would have divergence, divergence of the gradient of V is negative rho over epsilon naught. But this is nothing but Laplacian. And we were even able to solve it. Write that neatly enough. This required, from here to here, it required that V falls off to zero infinitely far away. So if V doesn't fall off, it's not a big deal. We have to use other means to compute the potential. We have seen this in the case of, certainly the infinite electric plane. V doesn't fall off, but we can still find a potential by integrating E. So if V falls off, we have a recipe for it. If not, we'll have to find it using other means. Fine. Now, this, that's already zero, so now I would get over here the curl of A is mu 0 J. So then I'll look at my inside cover and see this is equal to, what is it? The grade, and I just looked at it this morning, otherwise I certainly wouldn't remember. It's that minus del squared A. So this is the equation that you have to solve, as opposed to that. And then you're going, come on, this is one course. I'm going to learn how to solve one equation. That's it, we're done. Can't go beyond that. I don't want to know how to solve this one. And then you think to yourself, well, suppose I wanted to solve, I know how to solve that equation. Can I massage this into that? Turns out always yes. For that to happen, look, this is that. You can make it vectorial because you can do it separately for 3 components, that's all. So if this term didn't exist, we're good. Yeah? Then define a new A by, so this is the old A, right? Suppose you have a solution where there's a vector potential given to you. Unfortunately, the divergence of the vector field is not 0. So from that old A, we're going to create a new A. this lambda, in the language of campus scheduling of courses, is TBD. What does that mean? TBD? To be determined. Well, that's
Staff.
easy. Huh?
Staff.
Right.
So I know the instructions
Right,
staff.
right. And this could also refer to meeting times or even classrooms. If only solutions to exam questions could be TBD and you can submit it. So then, I want divergence of A to be 0. I'm going to force that. I can do that, well, if I can if I take divergence of A, I take divergence of this, and divergence of the gradient is the Laplacian. Well, that's equal to 0. That implies, whoa, that's again the only equation I know how to solve. Then I look at this, and I look at that. Even the minus is nice enough to show up. So I know the solution to it. Lambda, well, there's no epsilon naught. So it is 4 pi. If I define my new lambda to be this, because on this page it was TBD. Now we have determined it to be this. Then what happens? Again, we're assuming the original vector potential vanished at infinity. If we did it, we're going to find other methods of doing it. We can always find, so the vector potential is not unique. Is the electric potential unique? Up to a constant, because it's defined as the gradient of V. So if I take V and add 7 to it, it's also a new, we usually set it to where we want some place to be 0. That is convenient for us. Yeah? But vector potential is not constant. If one doesn't work, I can pick a new one by doing this. Now you might say, whoa, can we do this? If this is the old one, then this is B. What is the curl of the gradient? That should be just surprising to you. in quantum mechanics, the integral of A can be determined. It can be measured. But A is not unique. But the integral around a closed loop has to be same. You can see it's going to be the same. You can change, you can add to A0, you can add the gradient of any function. It'll give you the same magnetic field. There's something spurious about B that says B can be derived by from a more fundamental object perhaps, but that object is not well defined or is not uniquely defined. So these E and B fields have redundancies. Some of the terms are unnecessary. And that's a whole big problem in physics. Books and books, we understand it very well now. Yeah, it's called gauge theory. There's intrinsic freedom. You can do a vector potential, you can add the gradient of any function. Sinh x plus natural log, gradient of sinh x plus natural log of y. Just impossible functions. It'll give you the same magnetic field. But we won't jump into gauge theory, that's a whole production. The universe hasn't revealed to us in its simplest form. Anytime we define an elegant set of equations that describes the universe, it has intrinsic freedom. There are things about that equation where certain quantities that can be used to derive an expression for these equations are not uniquely defined. So for us, it matters not. This is not something we'll confront at all. I'm just chatting and wasting away. But I'm just telling you, wasting away, it's not really wasted away time, but imagine how interesting the universe is. There are certain functions that can be arbitrarily picked that generate well-defined equations for observable phenomena. There's a hidden world of functions that has certain freedoms that generate the same universe. So maybe 3 components of electric field and 3 components of magnetic field doesn't have to exist. If that freedom could be removed, we could live in a much more easier universe to calculate. We are not able to find that universe. We have to learn to live with this freedom, and this freedom gives us enormous structure and set of elegance and its own properties. It has a life of its own, it has a career of its own, but never a retirement, it seems. It just keeps, the field just becomes interesting and more interesting. That there are things that are not observed directly by us, but they determine the outcome of the universe, and yet there are freedoms there. From a bag of choices, we may pick any one of the candidates. Okay, so philosophically, this ought to entice you very well, but let me at least write down now the only equation I know how to solve, which was what? It used to be the gradient of divergence of A, well, we now pick it to be 0, minus del squared A equals U. And because we picked this choice, we get and then you go to yourself, aha, the universe is indeed defined by one equation. I can not only, I may have to write a code to integrate, but I can just tell you what it's going to be. It's going to be A equals, the minus goes away, there's a mu naught upstairs as opposed to this, so I get mu naught over 4 pi. This is a vector, this is a scalar, no matter, this is also a vector, so it becomes J. Now, again, this is from the Beard-Savat's law of three-dimensional currents. If it's, so I suppose I can put similarly. If it's a line current, I would have and if it's a surface current, would have that. But it's the same equation as you've studied in ENM1. So when we do problems, you won't have any difficulties. I don't know if Griffiths has already named this condition, and if he hasn't, there might be a reason why. Huh. Maybe there's another condition of potential vanishing. Eventually this will be known. This will be part of a condition called the Lorentz gauge. Sorry, Coulomb gauge, Coulomb gauge. That's the choice of divergence of A equal to 0. But there might be another condition on the electrostatic potential. That's why he hasn't mentioned. Because when we start doing electrodynamics, we need both the potential V and the vector potential A. So these four quantities will generate the electric and the magnetic field. You have to put them together. You cannot separate them. And that is a chapter and a half away.